Friends, good evening. On behalf of First Presbyterian Church of Berkeley and New College Berkeley, welcome to the third annual Berkeley Palmer Lectureship. My name is Michelle Vecchio Lysinga, and I have the pleasure of serving as the Minister for Christian Formation at First Pres Berkeley and a member of the Lectureship Planning Committee. As its name suggests, the Berkeley Palmer Lectureship was created in honor of the Reverend Earl F. Palmer, pastor of First Presbyterian Church of Berkeley for over 2 decades, founding trustee of New College Berkeley, an ardent scholar of scripture and society. Each year, the Berkeley Palmer Lectureship examines issues of concern to the church and academy by convening leading voices in biblical and relevant scholarship. The results? A dynamic forum for empowering students and leaders of all ages within the university, seminary, and church to think deeply, act justly, and live wholeheartedly as Christ's agents of renewal in the world. This year promises to be no less dynamic as our virtual forum enables us to gather with our guest speakers and one another from across the Bay Area, country, and world. Tomorrow evening, we will have the opportunity to hear from Dr. Ruth Padilla-DeBorst, theologian, missiologist, educator, and leader in missional formation in Latin America and beyond, as she examines with us the intersection of climate change, migration, and mission. This evening, we are joined by Dr. Jeff Reimer, whose distinguished research and teaching as the chair of the Chemical and Biomolecular Engineering Department at UC Berkeley will provide scientific context for our vital conversation this weekend. Thank you, Dr. Padilla-DeBorst and Dr. Reimer, for sharing from your important work in this critical time. We look forward to our formative and catalyzing conversations with you both. In the meantime, I invite you to look in your chat function. You can see capabilities for both closed captioning and how to engage with our speakers in a Q&A session following Dr. Reimer's presentation. In the meantime, to introduce Dr. Reimer this evening is Dr. Clayton Radke, Professor of Chemical and Biomolecular Engineering at UC Berkeley.
Hello, everyone. Good evening. It is a distinct pleasure for me to introduce a supportive Christian colleague, a brother in the faith, a distinguished researcher, and chair of the Department of Chemical and Biomolecular Engineering for almost 15 years now, which places him in the top spot for herding cats. His research is on quantum understanding of molecules using magnetic resonance spectroscopy. Now, if you don't understand what I just said, that's okay, because Dr. Reimer's commitment is to seek practical applications in the environment for his work. And he has been studying for the past decade now, maybe a little more, how to capture carbon dioxide from the environment for later sequestration. And he's going to share his expertise and knowledge of this field tonight with us. Professor Reimer has published over 200 manuscripts. He's been elected as a fellow of the American Academy and Association for the Advancement of Science, the American Physical Society, and the International Society for Nuclear Magnetic Resonance. Professor Reimer's title tonight is Our Changing Atmosphere, Evidence Says That Demand a Verdict. Jeff has won every teaching award on the campus at Berkeley, including the Distinguished Teaching Award, a very prestigious award. So I know we're going to have a great time tonight. For those of you who wish to ask questions that they come to mind to you during the presentation, please deposit them in the question and answer box, and we will deal with them in the question period. If we run out of time to deal with all the questions, Professor Reimer has kindly agreed to answer you personally. So we will get to your questions, even though we may not be able to share them all online. Jeff, the mic is yours.
Fabulous. Let's share the screen. Let's start with a movie, shall we? And the movie has a big cast of characters, so let me walk you through these characters. On the left-hand side of your screen is the concentration of carbon dioxide in the atmosphere in parts per million. In other words, not much. On this axis at the bottom is the place on the Earth where a measurement is made, as shown by these dots, the equator and the two poles. This red dot is particularly important. It's a measurement station on the top of a mountain in the Hawaiian Islands. And this measurement station is at the South Pole. Over here, we have more characters. Again, the concentration of CO2, but on this axis is time. And we're going to start a clock and we're going to look at how concentration in the atmosphere has changed as a function of time. And then the graph here in the center shows you where on Earth these locations are located. So you ready to roll? Here we go. So first of all, you'll notice the concentration of CO2 is jumping up and down. And here in Hawaii is the big red mark here showing how it oscillates in time, up and down. Over here, you see the South Pole oscillating, but a lot slower and exactly out of phase with the Hawaiian Island measurement. Here we are in the early 1990s, and look at the measurement stations coming online. And you'll notice that some of them are quite noisy. But even all of us can imagine what is happening with this line. On average, it is going up, no matter whether you're at the North Pole, the South Pole, or the equator. So let's follow this for just a couple more minutes. I think it stops at 2016. And as you probably know now, the concentration in the air today is 418 parts per million. Here we go, coming up on 2016. And then we're going to go back in time just from Hawaii, back to the mid-1950s or so. And now we're going to jump back in time using tree rings for measurement of the data. Now we're going to go back all the way to the time of Christ. And you see the concentration of CO2 in the atmosphere is much lower, 270 ppm. Now we'll use ice cores. Let's go back in time thousands of years, tens of thousands of years, 100,000 years, and let's see what is happening to the concentration of CO2 in the atmosphere. Remember, we're here today. And you see that it has gone up and down and up and down. And when it's down, that's what we call an ice age. Now, I just want to point out to you, as this movie progresses, the number of countries and the number of institutions within those countries that have contributed to these data. And this reminds you that the measurement of carbon dioxide in the atmosphere is an international activity conducted by friends, sometimes not so much friends. So the question, of course, that comes to mind, why is it going up? So here's a graph just from the Hawaii data. It's called a Keeling curve after Dave Keeling, the man who set up this station on the top of this island in Hawaii. The curve is named after him and received a National Historical Landmark from the American Chemical Society. And you know what I'm going to say? I'm going to say the CO2 in the atmosphere is rising because we're burning stuff. And elementary students of chemistry will recognize this familiar chemical reaction. A hydrocarbon, coal, natural gas, gasoline, and oxygen burn to form CO2 and water in the air. And this poses the obvious question. If our engines are responsible for increasing CO2 in the world, then we must be consuming oxygen. Now, the problem is measuring oxygen in the air is really hard, or rather measuring changes of oxygen on the order of parts per million is very hard because oxygen is 20% of the atmosphere. But it was interestingly enough, Dave's son, Ralph, who began his career making these measurements by taking the ratio of oxygen to nitrogen. And sure enough, the oxygen concentration is falling so that we are consuming oxygen as we burn our fuels. And if you're asking if the ratio of these slopes is the same, no, it is not the same. But one of Ralph's critical contributions in the 1990s was to recognize they shouldn't be the same, since a lot of the CO2 we put in the air is taken up by the oceans and by the soils. And if you account for that, then the stoichiometry matches. Our engines are responsible for the CO2. That's a mind-boggling concept. So let's jump to Eastern Germany, the Jenswalde power station, one of the miracles of modern coal-fired power plants, a 2-gigawatt power plant. And you can see here the cooling towers. This is not smoke from burning. This is actually steam. The smokestacks are hidden behind the steam. And the Jenswalde power plant is one of the power plants that's responsible for a significant fraction of Germany's power. We use coal even to this day, all throughout the world. So how much CO2 comes from this one power plant? Remember, we're trying to wrap our head around this notion of how could our burning stuff actually change the atmosphere? Students of engineering will recognize that a 3-gigawatt power plant consumes a certain amount of coal because of the heating value of coal. The power plant has a certain efficiency, so we need more coal than was calculated. And we can do these calculations and find out that the Jenswalde power plant consumes 25,000 tons of coal per day. That's a hard number to get your head around, so think of it this way. That's 218 railroad cars per day of coal, 24 hours a day, 7 days a week, 365 days of the year. That's a way to imagine how much coal this one power plant is consuming. So how much CO2 comes from that plant? Well, the chemistry students know how to convert burning coal to carbon dioxide. They know how to take the weight of carbon dioxide into a volume, and they know how to take a volume as a percentage of the exhaust gas. And here you have it, 3,292 cubic meters per second of exhaust gas comes from the Jenswalde power plant. Now, what cultural icon can we associate with a volume flow rate that large? Well, the answer is the Trump Tower. We can take the architectural diagrams. This is 300,000 cubic meters. And the Jenswalde power plant would fill the Trump Tower every 92 seconds. 12% of that is CO2. So that's one way to imagine our contribution to CO2 in the atmosphere. Let's take a further step back and ask, what about the concentration over all the coal-fired power plants in the world? And we have those data. So in 2017, 1,400 million tons of CO2 were emitted worldwide just from coal-fired power plants. Also a big number. Well, it turns out in that same year, we produced 344 million tons of plastic. To put that in perspective, we put into the atmosphere 4 times as much carbon as we did in all the plastics made in that year, just from coal-fired power plants. So the atmosphere is changing because we use the atmosphere as a receptacle for our carbon waste. Question is, how does the Earth cope with this? And in order for me to explain how the Earth copes with this changing CO2, I have to invoke a bit of a wonky diagram, for which I make some apology, but it's such a powerful tool for me to convey to you how the Earth responds to CO2. It's called a variance spectrum, and I'm going to demonstrate it first by talking about your mass, or I should say my weight. And on this diagram, you see on this axis is the change in your weight, plotted as a function of the time scale of an event. So for example, I eat 3 times a day. The time scale is 1/3 of a day, and my weight changes by this much. I also eliminate waste, and let's say that that's on the order of once a day. And so there's a time constant of 1 day and also a change in mass. And if I'm good, I will go to the gym, let's say every other day, exercise, expend energy and lose mass, and the time scale for that event is 2 days. And regrettably, as I've discovered, and maybe some of you have as well, as you age, regrettably, your body mass tends to increase. And so there's a long time scale associated with aging. So here's the variance spectrum of a typical human body mass, that it has these 4 peaks. Again, daily eating, daily elimination, exercise, and aging. Okay, let's take a look at the variance spectrum for the fluctuations of carbon dioxide in the atmosphere. So over here is a logarithmic scale for the change of CO2 in the atmosphere. And down here at the bottom is the time scale. So there's a peak that happens every day, some peaks that happen every year, a bunch of peaks collected around 10,000 years, and then there's a very long time constant. These are the ways in which the world copes with increasing CO2. And we know what they are. What happens every day? Photosynthesis. Plants take up CO2 from the atmosphere, and they change the concentration in the atmosphere by about a part per million. On the yearly time scale, what do these bumps do to? And again, I'm going to invoke the Keeling curve. And remember, we saw all those bumps in the curve that were happening? Well, those bumps are happening because if you look at those in detail, in the summertime, in the northern hemisphere, we are consuming CO2 because our plants are growing. And in the wintertime, the plants are dying, and CO2 from decaying plants is released into the atmosphere. Now, you're probably going to ask, how come it's not flat? Because the southern hemisphere has a different summer and winter. It's a really good question. Part of the answer is that much of the land mass is in the northern hemisphere, but it is also true that the northern and southern hemisphere airs don't mix very well. Also, if you're clever, you'll notice that we started the summer and came back again, and these levels are slightly different. And that's our contribution of putting CO2 in the waste receptacle of our atmosphere. Now, what about these peaks that are happening at 10,000 years? This is a very exciting area of study, and many talented scientists are looking at this. But how do we get the data in the first place? So this is a remarkable achievement in measurement science. So you go to a place like, for example, Antarctica, and you will dig down and get an ice core. Now imagine what has happened. In the earliest times, snow fell and collapsed down onto the ground. And in that snow was the air in which the snow fell. And then the next year, and then the next year, and then the next year. And over time, then, this snow compresses but preserves the composition of the atmosphere. So if we take little slices along these ice cores, we can date them with carbon dating and other methods, and then we get the concentrations of CO2. So that's how we get these long time scale measurements. And I do want to mention that this is a USA flag, a Russian flag, and a French flag. So what does that look like? Again, we saw that earlier. If you go back in time, in this case, about 800,000 years, you see these fluctuations. We call them ice ages. But all these data come from this sort of region of the spectrum. And what does that do to? Yeah, that's one of the most interesting problems in science today. It is certainly partly true to the fact that a large bolus of growing plant life in the oceans took up CO2. And as the ocean currents moved it and then descended it to the bottom of the ocean, as these ocean currents are inclined to do, that took with it the carbon dioxide that the plants had taken. And then 10,000 years later, that same bolus of water comes up to the surface again and releases CO2. So you have something like a 10,000-year cycle associated with the ocean currents. And that represents at least a portion of these peaks. So what is this carbon cycle at very long timescales? And that turns out to be a very important question for what the world will do after you and I die. So what do we know about the carbon cycle in the Earth? So it starts by rainwater and CO2 reacting together to form carbonic acid. You and I call that soda water. That soda water dissolves minerals on the Earth and brings them to the ocean as bicarbonate ions and mineral ions. And they precipitate as shells from the plants and things that grow in the oceans. So here's the big picture. CO2 weathers the rocks, comes down into the oceans as calcium carbonate or carbonates. And then plate tectonics will subduct a portion of that deep sea ocean into the deep interior of the Earth, where it is very hot. The reverse reaction occurs. We form silicates and the CO2 comes back into the air. And this cycle is hundreds of thousands to million years. The interesting thing about this cycle is, let's ask, how much carbon is in the atmosphere? Well, if I make that unit 1, then there's almost 50 times as much carbon in the oceans, 100,000 times as much carbon in the rocks, and look, 5 million times as much carbon in the deep Earth. So if we double or triple or 10 times the amount of CO2 in our short lifetimes, ultimately over this long time scale, that number will re-equilibrate with these and return back to the air as one unit. So here we have it. Now, the question is, what have we done, you and I? Where does our role in this variance spectrum play? So let's look at those historical ice core data. Remember, we're at 419 ppm today, and that puts us right about here, which is the contribution of combustion from humans to the variance spectrum. My friends, we are changing the atmosphere, and the Earth responds over many timescales. Now the question is, what about in our lifetimes? What are the consequences? And we need to look at these consequences in order to better understand what it is we can do to mitigate some of these consequences. The most obvious being temperature. This is the elephant in the room, isn't it? Global warming. And many, many entities have made many, many compelling graphs about temperature of the planet Earth. I took this one from a recent Science magazine because it's as simple as it gets. Here's measured temperatures for over 150 years. And as you probably know, 2016 and 2020 tied for the hottest temperatures in recorded history on the planet Earth. Now, the question you're going to ask is, well, isn't that just a coincidence? Maybe there's other things like sunspots. So let's ask a wonky physics question. Why is it that the Earth is getting warmer when CO2 is in the atmosphere? And to understand that, you need to imagine sitting down in deep space and asking how much energy flows from the sun to the Earth. And for that matter, how much Earthshine comes from our planet and goes into deep space. And these numbers are given by what's called a flux, and they would be an energy per area per time. So for example, watts per square meter per day, hour, week, month. And it's a fundamental truth of physics that energy is conserved and the Earth equilibrates with its environment. So if you measure the flux coming from the sun and measure the flux out in space coming from the Earth, the two have to be equal. And the way in which the flux adjusts is with the temperature of the planet, or for that matter, the sun. Let's do a thought experiment, shall we? Let's go out into space and put an umbrella up there so that it blocks some of the sunlight. According to this analysis, what's likely to happen? Well, the flux of energy from the sun to the planet Earth is going to drop because of the sunshade. But this equality then tells us that the flux of Earthshine into space will have to go down. And because the flux comes from the energy per unit time as T to the fourth, that means the temperature of the Earth goes down. This is not a silly thing, actually. It's an example of what we call geoengineering, which is that some people believe that the best way to cope with climate change is to introduce very large-scale experiments that drop the temperature of the planet. So what does this have to do with the atmosphere? So now we have to look a little more detailed. So here's the inlet from the sun. In these units, it's about 340, and a third of that or so is reflected back. And this means Earthshine has to be 240 in order for us to have been equilibrated with space. But if you look deep down inside of the planet, there's so many things going on. So for example, you know how much heat it takes to vaporize water, and every thunderstorm tells you, how much energy is released when rain condenses. So this is a very complicated problem. But if we were to introduce an umbrella now, blocking some, but not all of the Earthshine, and that's what greenhouse gases do. They absorb some, but not all of the Earthshine coming from the planet. What happens? Well, then the flux of energy coming from the planet drops by a little tiny bit, to be sure. And this balance is not even. And so the Earth responds by changing its temperature in order to bring this number back to 240. It's called radiative forcing. Earthshine, changes in the Earthshine force the temperature of the planet to change. That's a nice way to think about radiative forcing. Okay, so this is all theory, right, Jeff? Well, until 2015, it was largely theory. So what you had is some very talented scientists go into space and use infrared cameras and measure these numbers. And then they went down on the planet Earth and they used other kinds of infrared cameras to measure these numbers. And then they did the greenhouse gas measurements from, for example, Mauna Loa, that is in the Hawaiian Islands. And having made all those measurements, they can calculate the radiative forcing. and they can compare that to temperature. And you do this for 10 years. This paper was published in late 2015, the first convincing experimental evidence that radiative forcing changes the temperature of the planet. The red lines are the measurements on space and Earth of radiation forcing. The gray is the measured CO2 concentration, and the blue line here is the trend line for temperature. So my friends, our CO2 waste is warming the planet by radiative forcing. Now, what we can do with these kinds of data is we can go back in time and use mathematical models to calculate radiative forcing and parse the contributions of global warming to different things. This is a really lovely movie, or at least it is to me. So let me walk you through it. This would be the changes to the planet's temperature from changes in the sun's orbit over this period of time. Here's the change in the solar output from the sun over this period of time. And here is the change due to volcanoes. We're going to come up on the Mount Pinatubo volcanic eruption, which you may recall. So let's take all three of these together as the largest natural forces, and that's what nature would deliver to us in terms of temperature rise. What do you and I do? We mainly burn forests. We do put ozone in the atmosphere. And of course, we put aerosols. Aerosols are cooling, as you probably know. That's another geoengineering proposal. And here's the greenhouse gases, mainly CO2 and methane. And now we can put all of those together. I'll put it on the bottom of the screen for just a moment. This is the human factors that contribute to global warming. Now let's put everything together in one master plot. Here's all the factors that we've calculated compared to the data. And the extent to which the red line looks like the black line is the confidence with which we can use mathematical models to calculate what's happened in the past and, with some assumptions, to predict what happens in the future. So we have CO2 rising in the atmosphere from our combustion. It's radiative forcing that warms the planet, and we understand how to parse that warming into the various factors. Here's an interesting surprise for you. The Earth, in fact, has seen this before. Now we're not going to use ice cores or tree rings. We're going to have to use the shells of animals buried in the deep ocean. But we can get a plot, this magnificent plot that shows the deep ocean temperature as a function of time. Look at this, 70 million years ago up to the present day. So all those previous movies I just showed you were like way up here at the very beginning of this. So this goes way back in time. Here's the ice ages going back this far. Now, what is this? Look at this little jump here. That's called the Paleocene-Eocene thermal maximum. And it is a fascinating event 55 million years ago that portends what we're doing to our planet. So what we're going to do is we're going to analyze these seashells. We're going to look in particular at the isotopes of carbon and oxygen. And from the carbon measurements, we'll determine that a massive amount of CO2 and methane was released in the atmosphere, largely due to combustion. And that was about 4,000 gigatons compared to about 1,500 gigatons that you and I have placed into the air to date. A measurement of oxygen in the water tells us a proxy for temperature. And you see that at that time, the temperature of the planet jumped by 6 degrees C or 11 Fahrenheit. And that lasted 100,000 years or so. And just as interesting is there was a huge increase in acidity of the oceans during that same time. As I said before, carbonic acid is formed when you mix CO2 with water, and the shells of animals virtually disappeared during that window of time. And this whole thing was over in 100,000 years. What was the event? This paper, which was just published late last year, suggests with the best experimental evidence that the reason this happened was volcanic activity. This is what the Earth looked like at the PETM 55 million years ago. And I've included on this some numbers which represent temperatures in those portions of the planet. Now, first of all, a word of caution and honesty. The continents aren't in the right place, are they? That's because 55 million years ago, the continents have drifted since then. And so they're not exactly in the places you'd expect, but their features are clear. And you can see, for example, that Central America is largely underwater. as is the Amazon basin, as in Northern Africa. Much of Europe is underwater, and certainly Eastern China, the Eastern United States. And you'll notice that the ocean goes as far as Central California. And if you look at these temperatures, and remember that for San Francisco in the present era, the average day-night temperature is 14 C. So if you live during the PETM, the best place to live compared to today would, in fact, be Antarctica. So this is a logical asymptote of what happens with 4,000 gigatons of carbon. The atmosphere is changing. The change is due to combustion. Climate is changing. Radiative forcing connects these two together. And the Earth has seen this before, and 200,000 years will return to normal. Now, that may or may not be encouraging to you, but what I would suggest is we are interested in the consequences during our lifetimes, besides rising temperatures. So one of the consequences that goes with rising temperatures would be sea level changes. As you probably know, as you heat water, it expands. And so a warming planet would raise the level of the oceans. People have thought about this for a while. And in 2015, a very controversial paper appeared in the literature. A paper in which the global mean sea level, as measured by radar altimeters and tide markers, as a function of time, was plotted. And the authors figured out that the oceans are, in fact, sea level is rising at about 1 millimeter a year. Their controversial conclusion was that it's accelerating, and that if you look just in this window of time, it's almost double. Very controversial result from a group in the United States. So a completely independent group with different data sets from Europe did their own analysis, published it a year later, and indeed, they got the same rate and they got the same acceleration. So why is the sea level rise accelerating? Well, to answer that, we have to go back and ask, well, what's happening at the poles? What's happening at Greenland and places like that? And the answer is the ice is melting. And if you look at the contribution to our sea level from the melting ice just in Antarctica, you see that for this window of time, it's not much, but it's getting much faster because the ice in Antarctica is melting. Which is to say, for the better part of my life, sea level has been rising because warm water expands. But now sea level is also rising because we're filling the oceans with melting ice. Now, what are the consequences of rising water levels, particularly due to warming? So let's go back to that thermohaline circulation map. Remember, this is a map of ocean currents. You know this one, that's the Gulf Stream. That's what keeps Europe a habitable place in this part of the planet. And the water goes up and then goes down and gets cold and circulates around. So the water is not being heated evenly at all portions of the planet. And I call your attention to this portion of the planet over here, where warm water comes to the surface and circulates. So you can look at altimeter data, as was published a couple of years ago, and ask, what does sea level rise do around the planet? And you'll notice, for example, things look pretty good in California because we're constantly getting cold water from the Gulf of Alaska. But here, where the warm water comes to the surface, you see these big changes. And can I call your attention to this little point in space right here? You know about that point in space because the New York Times pointed out those are the Marshall Islands and they're disappearing. And the people need to go somewhere because their islands are going underwater. It is no small irony that the CO2 emissions from the wealthiest portions of the Earth are in fact displacing those that often have the least. What about some of the other consequences associated with climate change and rising CO2? And of course, the other one is weather. Now, I'm going to describe some results from a paper that was published a few years ago, but it's such a powerful graphic image, I think it's still important for you to follow. This comes from Jim Henson and his group. At that time, it was at NASA. Jim is now retired. But he asked the following question: how do people perceive of climate change? And in particular, what's the probability that the weather will be extreme? And so what they did is they compiled average temperatures from locations around the planet, and they made a bell curve for them. So for example, in San Francisco, the average temperature is 14 degrees C, and very, very few days is it much, much hotter and much, much colder. Wonks in the audience will recognize this as 1 standard deviation, 2 standard deviations, and 3 standard deviations, sometimes given the moniker sigmas. So the authors asked the following question: how much of the planet Earth has experienced a temperature larger than 2 to 3 sigma compared to a baseline? And the baseline is 1955 to 1981. So let's make a map. And the map is extremely telling. So if you compare 1955 to the baseline, you'll see that some places are cooler, extreme cool, some are extreme warm, but not so many. 1965, 1975. Are you ready? Here we are up to 2011, the last data set the authors analyzed. And as you probably know, 2017 and 20 were the warmest recorded temperatures on the planet. And in retrospect, it's obvious, isn't it? A small change in the mean has a very large effect on the tails. And if the planet is warming even a little bit, the extremes in hot temperature are going to prevail. So what about some other measurements of what are the consequences for rising CO2 in the atmosphere? How about inequality? Indeed, that can be measured and quantified. So here's a paper from some colleagues at Stanford. It was published a couple of years ago, in which the authors asked how much has global economic inequality changed due to global warming. This is not a future prediction, it's a looking back prediction. Because we know, for example, that these are the temperature changes on the planet compared to a baseline of 1986 to 2005. And you'll notice, for example, that the North Pole is getting a lot warmer a lot faster. And that's because ice normally reflects sunlight. And as you lose ice, more sunlight is absorbed and the effects are accelerated. So we know the change in temperature due to warming. And then we can ask, how has that contributed, or these authors asked, how does that contribute to, for example, the GDP per capita? And using these global climate models, the authors discerned, perhaps in retrospect, obviously, that cool countries benefit economically from warming because, for example, they can grow more crops, use less heat, and so forth. Whereas warm countries experience cumulative losses, mainly due to crop damage and the effects on humans due to warmer temperatures. So these authors can put it on a map. And here's the probability of economic damage associated with climate change during this window of time and just during this window of time. And lo and behold, no surprise to you in the audience, is it? Look where the most economic damage occurs. It occurs in the regions of the planet where most people live and many are poorer. How about some other consequences? Here's a good one. Does our behavior change? So let's imagine now that there's 2 young men and they're walking down a street in a small Italian town on a hot summer day. And one of them turns to the other and says, you know what, we should go into a pub because if we stay outside, we're going to get into trouble and have a brawl with those guys. Well, as you probably know, Tybalt does appear, Mercutio dies, and Romeo's intervention winds up killing Tybalt. Indeed, I pray thee, good Mercutio, let's retire. The day is hot, the Capulets abroad, and if we meet, we shall not escape a brawl, for now these hot days is the mad blood stirring. Did Shakespeare get it right? Are we more likely to be violent when it's hot outside? Or maybe better stated, are we more likely to be violent when it's hotter than average outside? My colleagues at Berkeley began a groundbreaking study and published it almost 7 years ago now. And first, we're going to look at this region of the planet and ask the following question. When the temperature is higher or lower than the average for that time, are we more prone to violence? So here, for example, in this brown patch is local violence in East Africa. And this is change in the conflict risk relative to the mean. And this is the deviation in temperature from the average for the norm for that time. Now, let's be honest with each other. These events at very cold and very hot relative to the mean are rare. So the shading is a measure of the error. But it's clear to all of us, isn't it? A 1 degree C above the mean has a significant increase in local violence. How about civil war incidents in this sub-Saharan Africa? And notice this temperature scale is different than this one. It only goes to plus or minus a degree. Same thing, higher temperature, more probable violence. How about the entire global tropics, and look at civil conflict onset as a function of temperature relative to the mean? Doesn't take a genius to recognize that when it's hot, we are much more likely to have civil conflict. Now, when I share these data and these results with students at Berkeley, some of them say, well, that's true for those people, but it's not true for us. And they would be wrong. So for example, here's violent personal crime in the United States, rape in the United States, violent intergroup retaliation in the United States. And to be sure, at the extremes, the error is large, but it's very clear that as we warm, we're much more likely to be violent. Now, I understand well the difference between correlation and causation, and I'm sure you do as well. But these correlations are profoundly disturbing, and law enforcement and militaries around the world take global climate change very, very seriously. What's another measure of violence? Well, that would be suicide. We are going to look now at a collection of authors who contributed to this work. It was published a couple of years ago from the USA, Chile, and Canada. And one of the things they started with was, what about our tweets? So they're going to look at 600 million geolocated tweets and analyze them for language that indicates depression. And perhaps no surprise, when the average monthly temperature is higher, that we are more likely to express ourselves in depression. And I want to point out this number, 68F, which doesn't seem very hot to you, but that's the average day-night temperature during that month. So what about suicide? And here's where the data is particularly alarming. To the extent that orange is bigger to the right of 0 than blue is the extent to which we are more likely to commit suicide when it's hot. Certain parts of North America clearly exhibit much more probable suicide events when it's hot outside. So we are causing the Earth's atmosphere to change rapidly. And there's a whole host of activities and consequences associated with that. And I just want to say that if you come to Berkeley and take my class and other classes, you could spend an entire semester just on these effects. And yet another semester talking about the biological consequences of these changing atmosphere. Like, for example, what's happening to plants and so forth. Now, mathematical models allow us to connect what we know now with what's happening in the future. I showed you how those mathematical models look back in time and do a very good job accounting for what's happened historically. We make some assumptions about economic growth and about how you and I contain CO2 emissions. And then from those assumptions, we run those models forward and see what the future consequences are for climate change. Now the first one, obviously, we'll look at the suicide data. So here we have in the United States by 2050 and Mexico by 2050, an additional tens of thousands of suicides owing just to the increase in temperature. How about, let's go back now and look at rising sea levels. So this paper, which was published in 2019, goes back and asks, what can we discern about the rising levels of ocean? And they're going to make an economic model. And I'm sorry, these numbers appear very technical, but I'll just say that they're looking at limiting radiative forcing to a certain number. They're talking about eliminating CO2 emissions by 2045, and also about implementing methodologies to get CO2 out of the atmosphere. So these are modest, not unreasonable conditions for dealing with climate change. And here we have the number of people on the Earth who are going to be exposed to flooding by 2050 under this scenario. So I want to call your attention to the fact that in this portion of the world, for example, tens to hundreds million people are affected by flooding. And the United States, 1 to 10 million people, and so forth. In fact, there are very few parts of the planet which are not going to be affected by flooding, even under this very optimistic condition. What else can we imagine? Well, these authors from these collection of countries decided to ask the following question, which is, what climates have humans lived in, worked in, and farmed in during the last 6,000 years? And it may come as no surprise to you that the kind of space we want to live in when it comes to rainfall and temperature is pretty narrow. Let's take a look at this square right here as an example. Here's where humans lived 500 years ago, so around the year 1600. And you see that we are in a very narrow temperature range, 10 to 20 degrees C, and a very narrow range of rainfall on the order of 40 inches per year. Humans now, humans 6,000 years ago, this is where we grow our crops. This is where we have our livestock. This is where our GDP comes from. And it comes then as no surprise that we live in a comfort zone. Now the question is, how does climate change affect that comfort zone? So these authors now ask, does climate change force us out of our comfort zone? Looking again at a map of the Earth. Here is the current comfort zones. So you see in certain parts of the United States, for example, down here in central Mexico, you have a high suitability. That is, we're very close to our comfort zones. Now, in the business as usual scenario, that is, we don't implement significant climate change mitigation. In 2070, this map has changed a lot, and perhaps it's best to show it as a difference. And again, you see large portions of the world in which many people live are now out of their comfort zone. Well, if we live out of our comfort zone, won't we want to move? And so this paper, which was published a few years ago, asked the following question. Can I use these mathematical models to estimate how far are you going to have to go and move to deal with climate change? That is, you live now in, let's say, for example, Lafayette, and it's getting too hot, and you wish to move somewhere where you experience the same kind of temperatures you experienced when you were living in Lafayette. That's the goal of these authors. And by the way, the model they're going to assume is that we keep to the Paris Accord, 2 degrees C. And as you probably know, as of today, we're not keeping to the Paris Accord. But if we were, this is the kind of thing we can do. Again, a little bit wonky. Please follow with me for a moment. This is my last technical part. So what we would like to do is use these global climate models to predict what the temperature around the planet is at the 2 degrees C scenario. So here's the surface temperature as a function of latitude. So I remind you, we're going to calculate the temperature of according to where you are up and down on the planet. So down here, past the equator, and up here, down here, past the equator, up here. And this is the surface temperature according to these mathematical models. Now, here's something Professor Radke will like. These authors look at this data and they take the slope at every point along this curve, and they make a new graph, which is the temperature change as a function of position on the planet. And then they take the slope along this axis to calculate the change in temperature per degree change in latitude as you move along the continents. Yeah, that's kind of wonky, and this graph is a little startling. So let's repose it in another way. This is how far you have to move, depending on where you live, in order to keep the same temperature you are today. And you can see that, for example, here at -15 latitude, you have to walk 1,000 miles to move to a climate that's similar to where you're at. And in fact, here's a better way to look at this distance. Now I use miles instead of kilometers, so we're all a little more comfortable. But look, there are portions of the planet where you have to go over 1,000 miles to get to the same temperature you're accustomed to in this 2 degree scenario climate. And even in the United States, and even in Western California, you still have to move some tens of miles or hundreds of miles in order to keep the same temperature. So the message is quite clear, isn't it? The pressures for migration under climate change are enormous. They're enormous from flooding. They're enormous from our perceived temperature changes. They're enormous because we're going to become more violent and our behavior more extreme. So what I could do right now, in closing, to open up for some question and answers, is I could say a technical summary. The atmosphere is changing, the change is due to combustion, radiative forcing, et cetera, et cetera. But allow me this one, perhaps a little more controversial way to express the closing of my lecture tonight. We extract stuff from the planet. We get minerals and coal, we get oil, and we get natural gas. And we burn those things. We burn those things to power our planet. We burn those things to have mobility. And we burn those things to make the trinkets that make our lives happy. And every person on this call tonight is profiting directly or indirectly from those processes. But there are consequences. And the consequences are we are warming the planet. And not everyone benefits from those consequences. And so, for example, in the Marshall Islands, they are building barriers to try and keep their land. So the question, my friend, is, would you please join the extraordinary mission to mitigate the effects of our carbon waste on the planet? Thanks very much for your attention. And Clay, I'm happy to pick up any questions now.
Well, I should be on, am I? Yeah,
think
there I am.
Yeah.
Good. I have no questions in the question answer period. So could people start populating questions to you, please? Yes. The first one is from Anonymous. How does the temperature affect our physical health in regard to illness?
So that is, so the answer is I don't know. I know people and colleagues who are studying this effect. And so, for example, let me take a step back and say, why are we more prone to violence when it's hotter? And people are asking questions like, what is going on in the brain in terms of the chemicals and the processes that are happening in the brain when the temperature is a degree or two above what you expect it to be based on your life experience? So there's neurology associated with that. The question I think you're asking is what other effects are present in the human body as the temperature warms? And the answer is people are investigating this, and I don't know the answer.
Thank you. Any other questions? Please, we have time. Well, of course, I always have questions, Jeff. You know that. So let me start with a toughie.
Good.
Non-technical. You have presented a large amount of data. It's sobering. Yet we know that our society is confused and conflicted on this issue, both with respect to what to do about it, and in some cases, does it even exist in the first place? So I ask a two-part question to you. What role do you think science, which is what you are, a scientist, play in this discussion? And second, what role does the church play in this discussion?
I thought maybe you'd give the easy questions to.
Well, I'm interested in the answer.
I think all of us, scientists included, tend to speak in hyperbole because we are passionate and we want to get a response. And social media and other means are amplifying that message. And we lack, at the moment, the capacity to sort of put a, if you will, a dampening capacitor on these feelings. And I think from my point of view of a scientist, when I talk to the public, as I have tonight, about science, I try very hard not to talk about what somebody else says about science. I'm trained enough to go and look at these original papers and discern from them the impact that I want to share with the public. So I'm not bringing you what I read in BBC or Vox or other kinds of media. I try to bring directly what's happening. And my friends on the Zoom call tonight, you are smart enough to look at a lot of these original literatures. And Clay will back me up on this. When you publish a paper in a journal like Science or Nature or PNAS, which is a year-long process at least, with the rigor of the entire community at you, you have to write in those papers an introduction and a conclusion that makes sense to an intelligent reader. And you all can read those And I would urge you to go to those places as opposed to places where you're comfortable, like Facebook. Now, what can the church do, Clay? Yeah, that's what I want to hear Dr. Padilla de Bourse say on Saturday night. There are many things that come to my mind, but I'm not a theologian. I know the limits of my capacity, and I really want to hear from the people who devote themselves to the scripture and devote themselves to the church to answer that message. But Clay, if I can just say one more thing about that, I'm going to maybe upset a lot of people on the Zoom call tonight and talk about the Pope. And I know many of you resent very much papal authority and perhaps the way in which the Catholic Church presents it. But I submit to you that the position of the Pope is a highly educated person who's extremely familiar with the scriptures. And our current Pope has made it very, very clear that that carbon, using the atmosphere as carbon waste receptacle is sin, and it has to be dealt with by the church in that way.
Thank you. There are a couple of questions that I'd sort of like to amalgamate that have to do with what do we need to do? For example, what changes do we have to make in order to meet the Paris Accord? What do you call us to do to engage in carbon capture? What might that look like in our own lives?
Yeah, let me share a screen for a second again, Clay. I had a feeling that question was going to come, so and I'm going to.
Not to call Becky to do that. I don't think I have the controls.
No, I do have the controls. I just have
Oh,
to.
you have the controls, yeah.
I have to play slideshow in window, select the window in my screen share. Excuse me for a moment. Screen share. Share. And open up this one. My apologies for the clumsiness. So what do we have to do? So there's what I call some low-hanging fruit, one of which is how we manage our soils and forests. There is tremendous capacity for us to adjust how we farm and how we grow things to take up a lot more carbon. It's not, it's been shown to be beneficial to the farmer and certainly beneficial to the soils. So there's public policy associated with how we treat our farms and whether or not we reforest the places we burn down. I know all of you hear a lot about wind and solar power. I won't say anything more about it because the media has made that very clear that carbon neutral energy production has to be part of our future. When we design and build buildings, we have to pay attention to how much energy they use. We can do that. The problem, of course, Clay, as I'm sure you know, is that an energy efficient building in its construction is more expensive, in its operation cheaper. I know a lot of you are very upset about the notion of nuclear power, but I do want to point out that the International Panel for Climate Change and many other environmentalists claim that in the short run, nuclear power can be a carbon minimal energy source, and we ought to think about that. We could use cleaner fuels. We've done that already. Actually, carbon emissions from coal in the United States have gone way down, but it's not because we divined climate change. It's because a natural gas has become so much cheaper than coal because of hydraulic fracturing or fracking. Yes, we can capture carbon dioxide from power plants, steam mills, cement plants, incinerators, and we can pump it underground safely. We know we can do that. That's only mitigating the current sources. Direct air capture, as Clay alluded to at the beginning of this lecture, is one way of achieving a negative CO2 concentration. I just will say that to do this and make a dent in the CO2 in our atmosphere would be the largest and most expensive engineering project ever conceived by humanity. Lastly, I just will say, Clay, that many people say I should be wagging my finger at the people on the call saying, you need to consume less. And, you know, I think it makes good sense. We all should be using less power than we need to. And when I talk to undergraduates, for example, at Berkeley, I'm astonished at the number of students who leave their computer on overnight, even though they're not using it. So there are things about personal consumption that are important. But I would also say that it is a funny thing about neoliberal economics and the conservatives of our time and the liberals of our time that blame us for climate change when in fact we need public policy.
Thank you. Here is two questions sort of amalgamated about the Paris Accords. One of them is, will we actually join? And what are the pros and cons? And if we join and meet them, will everything be okay, is the question.
The Paris Accord is a 2-degree C limit. And there's discussion about modifying that limit lower to 1.5. We're already almost at 1.5 now. So if we adopt the Paris Accord and we limit the global temperature rise to 2 degrees C, as I said in the lecture, there are still serious consequences, particularly for those who are in low-lying parts of the earth. And I think of Bangladesh, India, island countries, low-lying countries. The consequences for them are still pretty severe. So I'm not very optimistic, whoever asked that question, that we have any chance at all of mitigating some of the things that I talked about tonight. Do we have to join the Paris Accord? The message, if we do join, is that we are part of a community on the planet and the community together is concerned. We certainly can reduce our carbon emissions without joining the Paris Accord. And that's a question that perhaps others who are better trained in sociology and politics could answer.
Okay, let me now ask a question that's sort of related to your research, and maybe you could go off and discuss that a little bit as part of the answer to this question. That is there, well, what the question is there a potential for chemical removal of carbon from the atmosphere as opposed to sequestering it? I know you're heavily involved in this whole process, so give us a little more than just an answer. Tell us a little bit about what your work is like.
So capturing CO2 from the air is a challenging problem because it's so dilute. 420 parts per million is not much. And so what you're really asking is to run around with a butterfly net to catch a very small molecule out of a very large number of molecules. So a significant portion of my own research in my group is looking at materials that capture CO2 from the air. So for example, you open a box of baking soda, you put it in your refrigerator because it absorbs the smell of the onions, for example. Well, we're designing powders that absorb CO2 from the air. And you heat up the powders and the CO2 comes off. And so then the question is, well, then what do you do? Well, one thing you could do is put it in water and pump the seltzer water underground. And a recent set of data, past 2 years, a huge breakthrough has occurred in the geological sciences, where it has been shown that certain types of rock react within a year or two to produce chalk and take up the CO2. That part of the sequestration seems to be working. There is another challenge, which many of my colleagues in the College of Chemistry at Berkeley are working on, which is, can you make an artificial leaf? Can I use a powder, take up the CO2, and then use sunlight and water to create something useful for humanity, like fuel or food? And that's a challenging problem chemically. Leaves do it, but their efficiency is very, very low, and their complexity is very high. So many of us, myself included, are trying to figure out how to make powders that snatch CO2 out of the air and water out of the air and convert it into something useful. And that chemical reaction is hard to do. And so we're working on that. That's a significant problem. But one thing for sure is that in certain parts of the world, like for example, Iceland and the whole mid-Atlantic ridge, you can pump seltzer water underground with high volume and have it turn to chalk very soon.
Well, let me comment on this question. You need both concentration and sequestration. You can't get away with just one. Once you make it into a much smaller volume than 400 parts per million in a huge ocean of air, then you have to do something with it. So that's the second step. So concentrating it is a first step. In chemical engineering, we call this a separation process. And then you have to store it somewhere. So it's a two-part problem. Either one alone can't work. Okay, here's the next question. And we're getting a little away from your talk, but you'll handle these. What energy sources do we need to develop to meet our energy demand? Can we do it with renewables only, or do we need other sources, for example, nuclear? By the way, audience, when I described Jeff's work, I called it magnetic resonance spectroscopy. It used to be called nuclear magnetic resonance spectroscopy, and the first word has been dropped.
Yes, nuclear has a funny connotation, doesn't it? So I'm not researching this area actively myself. There are people at Berkeley, and as a concerned citizen and scientist, I try to follow this closely. It is certainly true that there are large reservoirs of untapped wind, in particular, that are available to the continental United States. And deploying that seems like a really wise thing to do. There's a lot of jobs there. And that's a lot of economic opportunity. Solar is a little more challenging because that takes up a lot of land, but there nevertheless are plenty of places we should be doing it. And if you don't believe me, just climb up on the Tilden Park and look down at the city of Berkeley and Oakland and El Cerrito and Richmond and look at how many rooftops there are. That's a lot of acreage for solar power, very little of which we're using. And if we are using, it's mainly to benefit ourselves. So solar's a low-hanging fruit, but wind is the big one. And right now, people are talking about offshore wind, Clay, at 1 or 2 cents a kilowatt hour. I mean, that's truly transformative. So that's a public policy question. I know many of my colleagues on the Zoom call tonight want to shut off the coal-fired power plants. My heart goes with you on that. I get that. The problem with shutting off coal-fired power plants is that the ratepayers took a loan to build that power plant for a 35-year lifetime. And that could be, for a typical coal-fired power plant, that's billions of dollars. So if we shut that plant down, who pays to finish paying the bills? That's a huge investment in money that the government would have to make to shut down a coal-fired power plant. So my personal view is I'd rather equip that plant with carbon capture and sequester that carbon and let the plant die a natural death. But I understand emotionally and technically that there's a tremendous will to want to shut down natural gas and coal-fired power plants. The advantage of nuclear is that we are, I think, accustomed to an energy economy in which we have concentrated sources and a distributed grid which takes that power out. So you can pull up the coal-fired power plant, drop in a nuclear one, and use all the same infrastructure. And it is certainly true that our colleagues in nuclear engineering have very, very clever ideas as to how to do the next generation of reactor design that produces far less, if any, radioactive waste that lasts for the tens of thousands of years we're dealing with now. So nuclear power is an option, but it's probably the most controversial thing an environmentalist could say because of the well-known criticism about radioactive waste, the safety and operation of these plants. And, you know, Fukushima did enormous damage to the psyche of the nuclear economy people, because here you have a highly technical nation, highly skilled workforce, and by design and operation, that plant was a disaster.
Well, my own personal opinion on this is that we must move carefully and slowly. It would not be wise right now to shut down all fossil fuel generation of power. It needs to be done carefully and thoughtfully and will take time. And it may be, and we don't know yet, nuclear may be a slide through sort of fuel as we move toward non-renewable to completely renewable. But I don't know the timeline. Do you have any idea, Jeff?
What I've read is that, you know, Gavin Newsom's, for example, his vision of having California carbon-free, and I think it's 2050, if I'm not mistaken, is certainly reasonable for California because we have a coastline, and the coastline has a heck of a lot of wind. And so, but if you're living in the Midwest somewhere, well, they have a lot of wind there too, actually. So let's, pick someplace a little further north or, other places. So, but I think, I'm not going to say in my lifetime, certainly in our children's lifetime, we could have carbon neutral energy. I notice there's some questions over here in the chat room, even though
Well,
people.
If you could transfer them over, I don't see them.
Well, I'll start with one called from Roland Peterson. What is the potential?
I addressed that one earlier about
Okay.
the carbon and the sequestration. I think I've got them all in the question and answer, and I'll get to them, Jeff.
Right.
Okay, here's the next one. And again, off topic, but again, I know you can deal with it. Most of us live in California, so we are aware of water supply issues. And their temperature is also important. Do you know of any convincing projections of where temperature and water supply might be in the comfort zone for food production? So I guess they're connecting water and climate and moving into comfort zones where you can also grow food, which is.
I heard a joke at a conference, Clay. Two scientists go into a bar and trying to decide where to buy property for retirement, and the answer is Winnipeg. And I think to answer your colleague's question, if you look at where water and temperature are going to become more optimal, it's definitely in Canada and Russia. And so, it's an interesting thing. Now, it turns out the projections I've seen for the Bay Area in terms of temperature are not so bad, because we're still going to have cool water from Alaska, although it won't be as cool, but we're not likely to suffer as much as other parts of the world. Our problem, of course, is water. And when it's so warm we don't have a snowpack, then water has to be mined from the air, it has to be mined from the ocean, and will contribute to the cost of our lifestyle. And as you know, Clay, there are places in California, Carlsbad comes to mind, Santa Barbara comes to mind, where they have built large-scale desalination to deliver, maybe not potable water, but agricultural water, but certainly they could deliver potable water. It's just going to cost money.
Well, Israel is heavily invested in this.
Of course, I forgot to mention Israel, indeed.
Yeah.
But, this is to Dr. Ruth Padilla DeBoer's lecture coming up. It's an interesting irony, isn't it, that countries like Israel and the United States, and Saudi Arabia, which can afford desalination, which can afford these tools, the Netherlands can build dams and dikes, but poorer countries cannot do that. Bangladesh is not going to have desalination plants, is not going to have dikes surrounding the country. And it is the poor and that suffer the most for a variety of reasons, not only because of geography, but because of economics. And to get back to your first question that I would like our colleagues to think about is, what is the Christian response to our starving and flooded out neighbors who seek to migrate for safety, who seek to migrate to live? What is our response?
Okay, another one on CO2. Can we plant our way out of CO2 problem?
That's actually not a silly question.
No,
I was at a conference just before COVID on carbon and climate change. And there's a very famous German scientist who's done an analysis and has estimated that if we plant 1 trillion trees, 1/3 of our emitted CO2 will be taken up. And, you're thinking 1 trillion trees is just no way. But of course, he and his team have arguments that indeed we could plant 1 trillion trees. We might have to encroach on some of the land we use to grow food, but maybe not. So can we plant our way out of this mess? No, but planting, and that includes management of our farm soils, could make a significant contribution to decreasing our carbon. Even more significant, perhaps, than switching from, one power plant to another. So yes, it's a very important thing to do. I've seen many studies that suggest this is something that should be our highest priority because it costs the least.
Well, here we butt up against the problem of population and area for people versus area for plants.
Mm-hmm.
That's something you haven't talked about because the demand for energy goes as population. Any words from your thoughts?
I'm reminded once when I told my mother I thought I was going to go into politics, and she told me, just don't ever talk about population control. And I think, she was reacting to what was going on at the time. Clay, you remember the population bomb, the book, Rachel Carson's Silent Spring. That was the era in which I was growing up, and it had a huge influence on me. But I have since learned that talking to people about whether or not they can have children is just not an effective way to talk about how to manage our planet, especially when people like many of us on the call occupy a great deal of space because we are privileged. And, I think that's the problem that's more easily addressable rather than looking at other people's and saying, you know what, you have too many babies.
We're coming to near the end, I think. A couple of more questions. One of them that relates to what we're talking about. Can you tell us more on the solutions available through soil management and changing in farming techniques?
Yeah, so for example, I'll give you one example that I know of. So right now, let's say you're doing farming, and what's typically done or what may be done is the husks from the wheat or the corn or whatever might be burned. Obviously, that contributes CO2 to the atmosphere. But you can make from those materials what's called char, which is to heat those materials up under vacuum or in the absence of oxygen. And what you produce are oils which can be useful for other products, producing chemicals and other things. But the char that's left behind is an extremely rich resource for the soils from which you grew those plants. So you put the carbon back into the ground to grow more plants. The yields go up, and the quality of the produce goes up. So each time you're thinning the field for husks and the like, you use char instead of just burning it. That's one example of how managing our soils could be more effective.
Well, there's a couple more questions, but I'm going to pick one that's a little bit controversial. It says, I was born and raised in Winnipeg, Manitoba. I used to pray for global warming. I've been up there in the winter too. Now that things are warming, this is a problem. Actually, you mentioned earlier in your presentation, there's a cyclical nature to temperature change. There have been ice ages that have come and gone. What caused the ice to have disappeared before there was much human causation? By the way, there are a lot of Reimers in Winnipeg.
Yeah, I know. My great-grandfather, great-great-grandfather, great-great-great-grandfather are all in a town called Steinbach, which you might know is not too far from Winnipeg. I've been there, visited many Reimer relatives.
This question is really one of anthropogenic nature of the CO2 question.
Right. So, we know well that there have been many, many cycles, and I tried to show them if you look at the CO2 in the atmosphere data for the past 800,000 years, you see these waves that are going up and down. And as I said, the origin of these waves is connected to the oceans. And more details people are still trying to figure out. It's probably one of the most compelling questions of our era, how oceans affect climate. But those ice ages are certainly due to the release and then uptake of CO2 from the oceans. And they go from 280 parts per million to a little higher and then lower and higher. And what I would say to your friend in the question is we're at 420 parts per million. We are so far above any swing in CO2 concentration from these historical processes that we are in really uncharted territory, with the exception of an event like the PETM. So yes, it's true. The planet, and by the way, the planet will cool off again. The question is, what are the consequences in our lifetimes? And what are the consequences for us as Christians? And, you know, that's, I think, the question really that's important for this weekend's conversation. So the answer is our CO2 is way, way out of historical norms going back 1 million years. And yes, there have been ice ages, and they come and go because the CO2 in the atmosphere comes and goes because of ocean currents and the processes contained within oceans. But we're way out of that range now.
Thank you. One final question. This is related to your geoengineering issue, although a little bit confused. What percentage do air pollution particles in the form of soot that fall and cover the northern and southern glaciers versus radiative forcing and warming are causing them to melt faster than normal? How can science mitigate either of these conditions? Is burning cleaner fossil fuels a step in the right direction? So I think this is a question of soot particles. I would have to break it into two parts: soot particles in the air, and then soot particles that have settled onto the glaciers.
It's an active area of research, and you know, people have pretty good estimates now for the competing role of soot in the air versus soot on the ground. It is certainly true that carbon soot on ice propagates the ice melting, but that effect is nowhere near large enough to account for the melting that's going on around the planet. So it's not just North Pole, not just South Pole, it's glaciers everywhere on the planet, even when there's very, very little soot. Greenland, the water emanating from Greenland is staggering. You know, millions of gallons a day are being released. Yes, soot is an important question, and we need some talented people to continue studying it, but the early effects, the early analyses suggest that this is an important but not critical role in melting ice. But I would also say we should have been using smarter combustion a long time ago. There's no reason for diesel to have soot the way it does, other than the fact that we have it, and it's cheap to produce engines that are dirty and more expensive to produce engines that are clean. But if you've been to Europe in the last 5 or 8 years, you know there's plenty of diesel trucks where you cannot see even a remote hint of soot coming out of those smokestacks. And that's because the Europeans have very strict standard on soot. And it's one of the proposals in the Biden administration that diesel trucks in ports, where there's a lot of diesel use, be modified to either burn clean fuel or use electricity. So soot is a big problem. It has been a big problem. And we should have been dealing with that a long time ago.
One final question. We've dealt with it, and I hope we deal with it the rest of this weekend. It says about 1/3 of an evangelical white community denies climate change. This was my question about controversy over what's going on. Probably greater than any other cultural group.
Yeah.
As Christians and as scientists, to what extent could we address this issue?
Yeah. Yeah, it's not just true about climate. Vaccination is another area that
Yes.
Evangelicals are much less likely to be vaccinated. And I think there's many confusing voices in our heads, not the least of which is the voice that says authority is bad and authority destroys humans. And that message is amplified when you imagine airplanes, emitting particles that make us sterile. I've heard that from an evangelical Christian, that contrails from aircraft are designed by the government to make us sterile. And it's such a difficult conversation to have when people, when we think the gifts of God don't include the ability for us to reason, that the gifts of God don't include the ability for us to act as a community. When you deny those gifts of God, then you're limiting the scope and nature of the Christian space to narrower and narrower windows. And, you know, Clay, I could easily see many of us going to the place where the church is like a spiritual shopping mall. We get the things we want to make us feel better about ourselves and leave the rest of the world outside of the mall. And I think that's just contrary to what I understand the Gospels to say.
With that remark, I'm going to bring the question period to a close. Thank you for your wonderful honesty and willingness to deal with some very difficult questions. Thank you so much, Jeff. Now let me call on Marianne White to tell us a little bit more what's going to happen this weekend.
Thank you, Clay, and thank you, Jeff, for a really stimulating exchange on a topic that certainly is top of mind. And we've learned so much tonight. Thank you, Jeff, for answering our need for good information, current and verifiable information on faithful stewardship in perilous times, and for helping us to frame the discussion for this weekend. Hello, my name is Marianne White. I'm a member of the Berkeley Palmer Lectureship Committee. Many people have made this weekend possible, beginning, as Michelle mentioned at the opening, with Reverend Earl Palmer, for whom the lectureship is named. Over 45 years ago, Earl had a vision for a forum in partnership between First Presbyterian Church of Berkeley and New College of Berkeley. And about 5 years ago, Reverend Dr. Tom Elson at First Pres and Dr. Susan Phillips, the executive director of New College, formed a team to continue Earl's vision of feeding and equipping the community for servanthood and leadership. We thank the members of the team who have brought us already leading speakers on biblical studies and racial justice. We're grateful to Dr. Ruth Padilla de Borst for accepting our invitation about 2 years ago and for her allowing us the rearrangements necessary to hear her lecture at last tomorrow evening at 7 o'clock. Many thanks for the capable staff of New College and First Pres Berkeley for gathering us all together and for investing many hours with meeting technology. Special thanks to the Graduate Theological Union for hosting the online webinars and the meeting tomorrow, and for their ready assistance with the unknown and unseen of facilitating such a forum on Zoom. The link that got you to tonight's meeting will give you access also to Dr. Padilla de Borst's lecture tomorrow night. Please also join us tomorrow at 2 p.m. with Dr. Reimer and Dr. Padilla de Borst for a deeper conversation with you. The link for the 2 p.m. meeting is in the chat. So, thank you all for joining us tonight. Bring your friends and we'll see you tomorrow. Tom?
Okay. So let me just say one thing to Jeff. Jeff, I think you are not only a scientist, but a theologian, as you shared on that last question so significantly and helpfully. Thanks, Clay. Thanks, everyone who participated this evening. I want us then to close with a word of prayer. Please join me. Lord God, we are thankful for the minds that you have given us. We're so thankful for Jeff's work, for the way that he helps us understand the significance of what's happening, not only to us, but to our often poorer neighbors in countries that don't have some of our own privileges and advantages. We love our planet. We love the waterways, the mountains, the plains. We love the fauna. We love all that you have given to us. And we want to be good stewards and take good care of it. Jeff has laid out some options for us in understanding, but also in acting. And so we pray that you would help us to take the next steps, to figure that out together, and to partner with any and all who want to take good care, be good stewards of your planet that you have given to us to live. We want to take good care of it, and we pray that you would help us do that. And tomorrow, as we sense even more the effects of climate change on people, on migration and other ways, we just ask that you would open our hearts and our communities to band together to make significant change in taking well care of your planet. We're thankful, and we pray this in Jesus' name. Amen. Amen. Thank you.